Hey fellas, welcome back to our OpenFoam show, OpenFoam series on heat transfer. So in the last video we were talking about a multi-region heater and the Joule heating solid, where we saw that we can introduce some voltage across some solid and we have some internal heat generation. So that was basically a Laplacian model with internal generation with two boundary conditions of 500 Kelvin, which were basically the heat sinks. And now today we want to talk a little more about using the chtMultiRegionFoam tutorial case. Alright, so I'm going to switch there very quickly, CD foam tutorials, and then we'll take a look at heat transfer, chtMultiRegionFoam, and we want to take a look at this Snappy multi-region heater. Okay, what is Snappy multi-region heater? So, well, okay. When I press list or L, it shows all these files out. So basically, I've actually run this case before. I've run this case before in parallel. So that's why you see this processor 0 to 5. And what is this actually? Well, in the last time we used a. All right, let me use paint to kind of illustrate. Last time, let's say this red box, we used this as a block mesh, right? And then we used toposet to define cell zones. For example, this was the heater, this was the right solid, this was the left solid, and over here we have the bottom air. I will just call it B, right? B. And then we have the top air in our previous heater case. So H, we call it heater, this one's the bottom solid, and this is left, alright, and this is right. Now, let's try again, right, alright. Okay, so how did we actually define this? We used toposet, and we used a box. We used a simple box with some coordinates to say, hey, I want to select this group of cells, and this group of cells should be called the heater zone. So that's why we have this box that we select a certain set of cells in the block mesh, and then we call it the heater cell set. Then this left solid is another cell set, this right solid is another cell set, top air is another cell set, bottom heater another cell set. And then okay, so how about more complex geometries? We can't always use simple boxes, right? So instead of using a topo set to define some cell zones or cell sets that we are going to make into cell zones, we can use this SnappyXMesh instead of a topo set in order to create our sets. So I want us to take a look at this. Now don't worry about all these logs, and normally we will have lots of columns where we normally see our stuff, but all the files are here. So let's go through them one at a time. We have our 0 original file, 15, 30, 45, 60, and 75. Then we have our all run, all clean, parallel, serial kind of files, and then we have our constant directory. Then we have all the logs that we have been running. Processor 0 to 5 because it's been running in parallel, and of course our system folder. And so I will want to. So just a recap, we have our usual files. We have our log files, 0, 15, all the way to 75, and then we have all of these over here. So what I want to do is basically copy all of this stuff over into the GitHub repository or directory. I think I want to git pull this. Okay, I want to remove the copy of the Joule heating solid and git pull just to double check. Okay, clear. Alright, I want to copy it here. So cp AR of whatever this is. Okay. That's a nice thing about having two terminal windows. So that should copy everything into there. So while it's copying, let's take a look at what's similar and what's different. So first thing we want to look at is to see the all run, perhaps the serial file. So okay, first two lines are of course the same, and remember we should have a hashtag !bin.bash in order for all these brackets to work. So I'm going to do a slight change of that first, because we were debugging in the last video and this was a big problem. So I'm just going to use the :W to write, which is to save. So cd blah 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 exit 1, and first thing it removes is the constant polymesh and sets. So this is probably part of what should have been in the all clean file. Alright, you can take a look at the all clean. So yeah, it says clean case 0 and it's supposed to remove a lot of all these things. Well, I think it should remove the polymesh sets as well. This will be pretty important because cell sets, they're talking about, like, you know, cell sets and everything like that. So let's take a look at what constant polymesh sets is like. I'm going to go to the right terminal. Never mind, I'll use the left one first. Let's go constant polymesh sets. Oh, let's see whether there's... Okay, there's nothing here in the polymesh. So, okay, since there's nothing there, yep, since there's nothing there, let's take a look at the rest of the steps of the all run serial. We are not doing parallel. Yeah, we are not doing parallel processing yet, because that adds another layer of, you know, complications. So we'll just take a look at what applications are run. First thing first, we have our block mesh, and these two steps I can kind of combine into one step. One is called surfaceFeatureExtract, one is called SnappyXMesh. So these basically, you know, take an STL file and, you know, cut it out of the block mesh in order to make the file. Okay, so let's take a look at what let's see. So again, I'm gonna look at all run file again just to check serial. Okay, so remember these two, as I was saying just now, surfaceFeatureExtract and SnappyXMesh is it's based on pretty much the same thing. So these two will have dictionaries in the constant, I think, system directory. Yeah, let's go to system. We take a look at 3 directories. One is 3 dictionaries. One is called Mesh Quality Dictionary, one is called SnappyXMesh Dictionary, one is called surfaceFeatureExtract Dictionary. So first thing they executed was surfaceFeatureExtract. So what does that do? It extracts from some STL file. An extraction method, it says extract from surface, right? So what does it mean? Usually for SnappyXMesh, it doesn't tend to do as well with edges. So if you have seen my SnappyXMesh tutorial videos before, you'll notice that somewhere, let's say you have some form of cylinder here. Okay, some form of cylinder here, and yeah, some form of cylinder. Let me erase this away. Yeah, some form of cylinder here, and what we notice is that if you have watched the SnappyXMesh videos, usually around the edges is where all the meshing problems start to occur. So the way to circumvent this is to do something called the surfaceFeatureExtract, so that you can take care of these edges which are so nasty to mesh. So this is what surfaceFeatureExtract does on a basic conceptual level. So extraction method, it says extract from surface, include angle. Okay, say mark edges whose adjacent surface normals are at an angle less than, include angle as degrees. So 0 selects no edges, 180 selects all edges. So for a flat, for a flat case, or rather, okay, let's take a look at it pictorially, so it's easier for us to visualize what's going on. Let's say you have a flat surface. So we have normals like that. One going up here. Okay. The other going up here. Okay. Alright, so these two, the normals are pretty much parallel to each other, right? So basically it means that this is one flat surface, right? This is not exactly an edge, but when you see the surface starts to bend, okay, so the normal is going to point this way, and this normal is going to point this way. Now what is then the angle between the normals? So I'm just going to use a brown. Okay, I'm going to draw it all the way down, like so, just to give you a feel of what's going on. So this is the angle theta. Okay, this is the angle theta. We see that this is a non-zero angle. So you can see that this is defined as an edge. So if this angle theta is, for example, specified here as less than 150 degrees, so if it's less than 150 degrees, it will select it will mark all the edges that are having theta less than 150 degrees. So basically, if we have, yeah, I think most in a cylinder case, for example, right? In a cylinder case, I'm just going to draw a very crude cylinder with a line across it, because the box function is very easy to draw. So in a cylinder case, usually the maximum the edge angle is about 90 degrees, right? So one normal is going to go here, one normal is going to go outwards towards you, and that is going to be a 90-degree angle. So if you say, okay, I'm going to just do 180 degrees, 150 degrees, that should cover all these edges, right? All the edges here. So it will mark out this entire rim, because this entire rim is an edge. Okay. So what it then does is to mark them out and then write into an edge mesh or something like that. So let's see. We should be able to see in maybe the heater. Okay. Maybe. Let's do this. Just like the other videos, I'm just going to do an all clean. Alright, I'm going to do an all clean. And then we'll run the steps one at a time. Then we can see what effects are actually going on. So I'm going to do an all clean. And the first step in the all run serial. So we're going to remove all the polymesh.sets. Constant polymesh and sets. If there's nothing there, then it's okay. And we're going to run block mesh, blockmesh.log. We know what block mesh does, so don't really need to do anything about that. Let's run surfaceFeatureExtract. So how do we run surfaceFeatureExtract? Let's take a look at the log.surfaceFeatureExtract. And all they tell you to do is just do surfaceFeatureExtract. Okay, so let's run surfaceFeatureExtract, and I'll put it in surfaceFeatureExtract.log. So yeah, let's take a look at surfaceFeatureExtract.log, and it's going to take the surface from geometry.stl and it puts the output as geom. So it's going to put all these edges. So where's it going to write it to? It says writing 20 internal edges to wherever our file directory is constant extended feature htmesh geom blah 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 dot object. Okay, so all these obj files are in the constant directory, and we see this extended feature mesh. All of them are here. So let's see whether we can open them up with ParaView to see what these edges are about. I believe obj files are viewable by ParaView. Okay, I'm going to come up from here to navigate to Snappy Region. I'm going to constant and extended feature mesh. Oh. Okay. Maybe it's not viewable by ParaView, but regardless, let's take a look at whether we can let's see whether we can open this up. Okay, we can. So extended feature htmesh, we have a geometry, and then these are, I guess, all the coordinates of where the edges are. Okay, so geometry, concave. Okay, so we can't VI these OBJ files. Okay, yeah, so ParaView can't open the OBJ files for some reason, but okay, maybe Paint 3D can. Let's open. Back. Menu. Open. Browse. Okay, so we want to look at desktop. I'm going to go through the shortcut, and I want to take a look at our Heat Transfer YouTube, chtMultiRegionFoam, Snappy Multi-Region Heater. Let's go to look at constant. Extended feature htmesh. Yes. So let's take a look at internal edges. Oh, couldn't open. Okay, forget it then. Okay, regardless, never mind. We could not quite visualize it. Though Paint 3D is supposed to be able to open that, or ParaView for that matter. But never mind. Okay, so basically what we need to know is what all these OBJ files are talking about. They store the information of the edges so that we can do a SnappyXMesh properly. Alright, so that's surfaceFeatureExtract. Now let's take a look at the next step. We see run application SnappyXMesh override. So this is interesting. Okay, let's take a look at the log.snappyxmesh. Alright, so okay, how do we run it? We run snappyxmesh parallel decompose parallel dictionary system decompose parallel dictionary 6 override. So this thing is being run in parallel using this decompose parallel dictionary, which is quite interesting. That's a way we can run in parallel without reconstructing the parallel dictionary. Okay, so this is the other way to run SnappyXMesh in parallel. Oh, this is something new. Yes. So we learned from this tutorial case we can run SnappyXMesh in parallel without doing this whole decompose parallel dictionary beforehand. So what I mean is this. Normally we have to do this, run application decompose dictionary parallel. Okay, maybe I got it wrong. Okay, doesn't matter. Okay, so this was run in this case was run in parallel, not series. Okay, my bad. Alright, let me try and run this case in series, and then we'll see what happens. So I just did an all clean. I'm gonna fast forward the running of the all run serial. So it's running block mesh, SnappyXMesh, split mesh regions. Alright, so it's running change dictionary as we are pretty familiar with before. Okay, so now let's take a look at the log.snappyxmesh as the thing is running. So it just says snappyxmesh override. So this is something we are more familiar with. We are not going to mess around with parallel dictionary. So yeah, what is snappyxmesh doing over here? Okay, so we'll take a look. It's creating time and it's making a mesh for time equals 0, read mesh in this time. So overall bounding box is this. It's reading the refinement surfaces, which we can take a look what those are later. And very important, remember when we are talking about the surface feature abstract, this is what we were actually talking about. Say reading features, read extended feature chtMesh, geometry, extended feature chtMesh. So these are like 230 points which we saw just now. And this is how all the edges are defined. They are being read properly. The refinement level goes according to the distance based on this geometry. Extended feature chtMesh, 230 points, 244 edges. So this part actually deals with very much the edges that we are talking about just now. So it's going to do this and it's going to add patches. Alright. And then the refinement phase, yes, we have talked about it before, what refinement is. If you're not sure, please go and watch the OpenFoam intermediate tutorials inside the description, the playlist in the description. So this is the surface refinement, etc., etc. It should be very quick. All right. Okay, so now the next thing is to, after the refinement is done, splitting the mesh at the surface intersections. Just introducing baffles that are introduced for all this. Okay, so it's gonna split it up into several cell zones. See, for cell zone, blah 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 blah, we will have some sort of points in there. So all you have to do is to supply the correct STL file, and you tell snappyxmesh, hey, in this enclosed region, and this coordinate is inside this enclosed region. Alright, so if you're not sure, I think, for example, okay, I just do very simple one. So let's say you have an STL file like that. I want to call this region 1, I call this region 2. I need a coordinate, a point inside region 1 that is defined by the x, y, and z. Okay, x, y, and z. And if I want to define the region for point 2, I will also need a point called x, y, and z. Alright, so I'm just going to draw a small little dot there, and there goes x, y, and z. Okay, so for now I'm going to stop because the video is going to get long, but hopefully just can see how this case is being structured. We talked a bit about the surface feature extract and snappyxmesh and how it's being used to define different cell zones, which we can then use to split the mesh regions up. Thanks for watching. We'll continue our discussion in the next video. See ya.